So we have looked into one kind of vacancy point defect, which is vacancy. Now, another kind of point defect is a self-interstitial point defect, and it is a defect in which an atom from the crystal that should have been there in the normal position is crowded into an interstitial site, that is a small void space that under ordinary circumstances is not occupied. Vacancy is when an atom is missing from the position where there should have been an atom. A self-interstitial point defect is a defect in which atoms or atom move from its original position and gets trapped into an interstitial site or a site which is a small void space that is normally not occupied in a crystalline perfect order crystal structure. Now, if you see here, you find an atom tightly bounded in a space where this atom should not have been placed. These spaces between the atoms, they are the interstitial spaces, small interstitial spaces, which are generally not occupied by the atoms. These are the empty spaces. If you remember the atomic packing factor of 0.74 or 0.68, you know roughly 70% or 72% in BCC is the empty space within a unit cell. And these spaces are basically made up of these interstitial voids. So if an atom gets trapped into this interstitial site, this is known as a self-interstitial defect, point defect. As it says in metals, a self-interstitial introduces relatively large distortions in the surrounding lattice because the atom is substantially larger than the interstitial position in which it is situated. So यहाँ पे बीच में जो एटम है वो बड़ा धक्के चुक्के मार के अपने आप को घुसाएगा, because although the space, the comfortable space for the atom is not there, it is not desirable for the atom to be here. The space is not designed in such a way. But if an atom gets entrapped into this space, ये इस region के अंदर एक stress create कर देगा. ऐसे ही है जैसे हम we were sitting on benches with comfortable spacing, and there's someone who comes in into that space and start to make space for himself. He would create stress in the surrounding region. सारे जो बैठे होंगे वो तंग हो जाएंगे. So similarly, an atom when it tries to occupy a space which is not designed for its positioning, it would create a distortion or a sort of stress in its vicinity. All right. And since there is not much space for atoms to be placed in the interstitial location, the formation of this defect is not very highly probable. There is little probability of this sort of defects, and it exists in very small concentrations which are significantly lower than that for vacancies. Vacancies essentially are easier to create. These sort of defects, the self-interstitial defects, they are relatively difficult to create, having low probability, and the amount of these defects is significantly lower than that of vacancies. Then comes another type of defects, which is substitutional point defect, and we'll come to that. It says that a pure metal consisting of only one type of atom just isn't possible. It is very rare to have 100% pure element. Impurity or foreign atoms will always be present, and some of them will exist as crystalline point defects. For instance, in alloys, impurity atoms or foreign atoms are intentionally added to impart specific characteristics to the material. So if we have one relatively pure material, you normally add foreign atoms to that material in order to get some desired characteristics in the material. For instance, sterling silver is a famous known name for silver or an alloy is silver, in which there is 92.5 weight percent of silver and 7.5% of copper, weight percent of copper is added to this silver. In normal conditions, silver, which is highly pure, is highly corrosion resistant, but is also very soft. It resists corrosion, but pure silver is very soft. So 7.58% of copper is added to sterling silver or pure silver, which significantly enhances the mechanical strength of silver and without compromising the corrosion resistant property of silver. So at times, as I mentioned in the introduction, defects are created in order to improvise certain properties of the material. Now, the addition of impurity atoms to metal will result in the form of solid solution. We have heard the term solution so many times, but solid solution is a term which we are not familiar with. What is a solid solution? We'll be looking into that. What kinds of different solid solutions are there? And they are characterized, essentially characterized as defects because these solid solutions disrupt the perfect crystalline order. In solid solutions, as in the normal solution, sorry, are you guys able to hear me?
Yes, sir. Yes, sir, we are here.
आ
Is
रही है
it
सर आपकी
crystal
आवाज
clear?
बिल्कुल ठीक मुझे तो ठीक आ रही है सर
Yes, sir.
अगर कुछ लोगों को ठीक आ रही है तो that means बेटा you'll have to check up with your internet connection or you'll have to refer back to the recording. All right.
Okay, sir.
So in terms of solid solution,
सर अब आपकी आवाज में डिस्ट्रैक्शन आ रही है.
जी सर अब आ रही थी
यस सर, अब आ रही है.
जी अब सही है.
अब
There was an internet, all right, internet got disconnected, so that was the reason. All right, so solvent represents the element or compound that is present in the greatest amount. On equation, solvent atoms are also known as host atoms, and solute is used to denote element or compound present in the minor concentration, just like in the normal solution. Solid solution, it's an extrinsic point defect. So far, what we have looked into vacancy and self-interstitial defects. They are intrinsic point defects. That means they are the defects that are dependent upon the original material. Solid solutions are basically extrinsic point defects because there is something which is added to the material from the outside. All right. There is an external factor that is associated with the solid solutions. In solid solutions, you have two or more elements which are atomically dispersed in a single phase structure. That means the crystalline structure remains the same. Their structure would have its own lattice parameter.
Excuse me, sir.
जी
सर ये सॉलिड सोल्यूशन और अलॉयज एक ही चीज है ना?
जी एक ही चीज है. Solute atoms are added to host atoms, and let's see if we have these atoms. These are the solvent or host atoms, and you have these smaller quantity of solute or purity atoms. These are the of your mic. Thank you. Now there are two possibilities in solid solution. It says two outcomes for metallic solid solution of B in A. Solid solution means random distribution of point defects. That means A is distributed in the B matrix randomly. One of the outcome is substitutional solid solution, for example, copper and nickel. The gray atoms are of nickel, and at certain positions, copper atoms have replaced or substituted nickel atoms randomly. This is the substitutional solid solution where the host atom the position of the host atom gets substituted by the foreign atom. For instance, copper and nickel. The other sort of solid solution is an interstitial solid solution. In this case, the host atom remains at its place, and the foreign atom, it occupies interstitial sites. For example, carbon in iron. Now, if you see iron, the atomic radius is much bigger. Carbon, the atomic radius is much smaller. So this is a possibility that instead of taking the space of the atoms or substituting the parent atom, carbon gets the interstitial sites. It gets occupied in the interstitial sites. Now, if I ask you, just or before that, crystal structure is unchanged, but the lattice distortion may be there. Since there would be difference in the size of copper and nickel, there would be some atomic mismatch, or there would be some disruption in the bonds. Similarly, if there is no carbon and if there is carbon inserted into the space, there would be some distortion or stresses created within this space. All right. So although the structure would not change, but there would be lattice distortion that would be there. What do you think? Would the solute atom affect distortion or the effect of distortion? What is your point of view? Does the size of solute atom would affect the distortion in the lattice?
Yes, sir.
Yes, sir.
Yes, sir.
Alright, कैसे affect करेगा?
सर अगर ज्यादा हो तो स्ट्रेस ज्यादा होगा, वो जो आप स्ट्रेस का वर्ड यूज कर रहे थे, इसी तरह सर जैसे आपने कुर्सी की मिसाल यूज की, मोटा बंदा हो वो ज्यादा स्ट्रेस को करेगा.
Very good, बिल्कुल exactly, very good. So yes, the size, the greater the size, the higher would be the distortion. Now, for substitutional solid solution, if there has to be a substitutional solid solution, there has to be certain conditions or criteria that has to be met. Copper nickel को replace कर रहा है. क्या carbon solid solution बना सकता है nickel के साथ? Is it possibility that copper, since copper is forming a solid solution or substitutional solid solution with nickel, is there a possibility that carbon would form a substitutional solid solution with nickel? We'll have to look into the conditions which are known as Hume-Rockström rules, which are the conditions for substitutional solid solution. The first condition says that the difference in the atomic radius of the solvent and the solute should be less than 15%. So atomic radius should be close to each other. If the difference is more than 15%, then you cannot have the substitutional solid solution. This is the first condition. Then you have another condition that the solvent and solute should have similar crystal structure. If it is FCC, it should be FCC. If it is BCC, it should be BCC. The third condition is proximity in the periodic table. That is similar electronegativity values. It further says if there is large electronegativity difference, then the metals would form intermetallic compounds rather than substitutional solid solution. Compounds means that the replacement would be in fixed ratio, Al2O3. That means for 2 atoms of aluminum, there would be 3 atoms of oxygen. In substitutional solid solution, there is no such condition. It's a random distribution. You could have copper, nickel, solid solution, substitutional solid solution. Let's say copper is 5 weight%, nickel is 95 weight%, copper is 10 weight%, nickel is 90 weight%. There is no restriction on the amount, although there is a restriction, but there is no fixed ratio in which this solid solution would form. All right. But in terms of intermetallic compounds, there is a fixed ratio that the elements would have to follow. The fourth condition is that valency. Same valency elements are favorable for extensive solid solution. If there is similar valencies, it is highly probable that the solid solution would be or there could be large amount of substitution that could take place. Now, based on these four rules, this is a table which has elements, atomic radius, crystal structure, electronegativity, and the valency. Based on these four conditions, what would you predict? Which elements would form substitutional solid solution with copper, or which of the few elements would have higher probability of forming a substitutional solid solution with copper? So if copper is your solvent, which of these elements do you think would be most appropriate to form or to become the solute? Yes.
Nickel.
All right, I have got one option as nickel. Any other option?
Zinc.
No, sir. No, sir.
सर लेड भी हो सकता है
Where is
Yes, sir.
lead?
सर निकल के नीचे
This is platinum. Lead is Pb.
अच्छा सर सॉरी सर ओ वही पीडी
Platinum भी sir हो सकता है sir.
All right, let's say platinum. Someone said zinc.
सर आयरन हो सकते हैं.
Zinc के बारे में क्या ख्याल है? और someone said iron. Iron के बारे में क्या ख्याल है?
No, sir. इनकी crystal structure is different है ना.
Very good. So first thing is atomic radius difference is atomic radius is less than 15%. The second thing is similar crystal structure. Copper is FCC. Iron is BCC. So no. Zinc is HCP. So no. All right.
Yes, sir.
So the probability of forming substitutional solid solution with copper would be that of nickel having the highest probability and then that of platinum, because the crystal structure is same, atomic radius is less than 15%, valency is same, and electronegativity is in case of nickel is much closer, platinum is not very far away. All right.
एक्सक्यूज मी सर, इस तरह तो एल्यूमिनियम का भी जो स्ट्रक्चर है वो एफसीसी है और वो भी 15% से कम है.
Have you calculated?
उसकी वैलेंसी 3 है ना.
उसकी वैलेंसी भी चेंज है और इलेक्ट्रोनेगेटिव डिफरेंस भी है.
There are multiple things that are going far away. If you compare with copper, atomic radius, much different, electronegativity, much different, valency, much different. So all the parameters they are moving towards the or moving against the provision that has been provided by the rules. Clear?
Okay, sir.
Yes, sir.
All right. Moving on. Interstitial sites are very small due to high packing density of metals. You already know for FCC the atomic packing factor is 74%. So the metals are very highly packed. Solute and solvent have large size difference. You should have very small atom as compared to the host atom in order to have interstitial solid solution. Copper and iron, we have already seen the example. Interstitial defects are again less frequent than vacancy defects. All right. Moving on.
Yes, sir.
Towards the composition of solid solution. Now, Normally, compositions are expressed in terms of weight percent. When we say composition, we mean that there is a solvent and solute present. Weight percent, when we are saying weight percent, or when we're referring to composition, we know that there are two or more than two elements involved. So when we are talking about weight percent of the element 1 in a material, we are basically referring to the mass of element 1 divided by the total mass multiplied by 100%. Similarly, mass of component 1 or element 1, mass of element 2. If we have to find out the composition in weight percent for the second element, we'll have mass of that element divided by the total mass multiplied by 100%. This is weight percent. Sometimes the composition is expressed, or most of the time it is expressed in weight percent. There are times when the composition is expressed in terms of atomic percent. And in atomic percent, we are not comparing the atoms. We are essentially comparing the number of moles of element 1 divided by the total number of moles multiplied by 100 would give you the atomic percent of an element in a material. Clear enough?
Yes, sir.
All right. At times, you have been given with weight percent and you have to convert it into atomic percent, or at times you have to convert atomic percent to weight percent. In such a situation, these are the relationships that you could use. First is the conversion of weight percent to atomic percent for a two element alloy. That means if you have to find atomic percent from weight percent, so you would use this relationship where A and A1 and A2, they represent the atomic weights of element 1 and element 2. This is conversion of weight percent to atomic percent. If you have the other way around, conversion of atomic percent to weight percent, you would have this relationship. That means the weight percents would be replaced by atomic percent. Clear enough? Is it clear?
Yes, sir. Yes, sir.
Now, moving on, we'll look into two examples and I'd like you to solve this example. This is finding the equilibrium number of vacancies per cubic meter, where electron volt per atom is given to you. If you want, I can give you the temperature is given to you, the energy for the vacancy formation is given to you, atomic weight for iron is given to you, and the density is 7.65 grams per centimeter cube. Atomic weight is 55.85 grams per mole. Avogadro's number is 6.02 into 10 to the power 23 uh, atoms per mole, and the Stephen Boltzmann constant is essentially, the value is 8.62 into 10 to the power minus 5 electron volt per atom per Kelvin. The formulation is N over NV equals to exponent of minus QV over KT. Now I need you to find out the NV per meter cube. This is what you have to find out. Number of equilibrium vacancies per meter cube at 855 degrees centigrade. Have 5 minutes, quickly solve it out so that we move on towards the next example. We have already solved a similar example. This is for your practice. I'll share the solution once the 5 minutes are over. I cannot give you more than 5 minutes since we are running out of time. All right.
Okay, sir.
Sir, done.
Great. I still have 3 minutes left, so I'll let everyone else do. All right. Very good. जी 1 minute left. बाकियों ने भी किया किसी ने और?
Yes, sir, कर रहे हैं.
ये सर
All
कर
right.
लिया.
All right. Great. 1 minute. I'll share the solution after 1 minute. All right, let's look at the solution now. So what is the answer that you've got?
सर मेरा तो 1.5 into 10 to the power -5 है.
So 1.236 into 10 raised to the power 24.
सर 1.237 10 raised to the power 24.
This -5 should
सर
be
मैं असल में मोबाइल में भी काम कर रहा हूँ तो इसलिए भी हो सकता है सर मैं असल में मोबाइल पे कैलकुलेशन कर रहा हूँ तो इसलिए भी हो सकता है.
In any way, ये जब जैसे ही आंसर आपके सामने है ना 10 to the power -5, this should be an alarming sign for you for vacancies at 855 degrees centigrade. This should indicate that कि कोई मसला है. But anyways, since you are using the mobile, we can expect that. So those who have got 1.2 into 10 to the power 24 per meter cube, they are correct. All right. Similarly, this is basically, sorry, the number of atomic sites, and this expression over here is the expression that for which you have to take the exponent, and you just have to multiply. Clear enough? Remember, we have multiplied centimeter cube by 10 raised to the power 6 to convert it into per meter cube. Now, the last numerical that we'll be looking into is essentially regarding the composition or atomic person. It is given that you have 45.2 kg of copper, 46.3 kg of zinc, and 0.95 kg of lead. And you have to find the atomic percent of these three elements in this alloy. So what is the formula for atomic percent?
Sir, C1 is equal to number of moles of mass 1 over number of moles of mass 1 plus number of moles of mass 2.
ओके, अब मुझे ये बताएं कि इसमें आपको व्हाट इज द नेसेसरी इंफॉर्मेशन व्हिच इज रिक्वायर्ड?
सर यहाँ पे mass दिया हुआ है, हम इसका मोलर mass निकालेंगे और number of moles निकाल लेंगे.
वेरी गुड. So essentially what you will be doing is that आप individually हर एक के moles निकालेंगे. Mass of copper divided by its atomic weight would give you the number of moles of copper. Mass of zinc divided by the molecular weight of zinc would give you the number of moles of zinc. Mass of lead in gram divided by the number of atomic weight of lead in grams per mole would give you the number of moles of lead. Once you have the individual moles, it's simply moles of an element divided by the total number of moles. So moles of copper divided by the total number of moles multiplied by 100% would give you 50 atomic percent of copper. Similarly for zinc, number of moles of zinc divided by the total number of moles multiplied by 100% would give you the atomic percent of zinc, and number of moles of lead divided by the total number of moles multiplied by 100% would give you the atomic percent of lead. Clear enough?
सर अगर मतलब अब तो तीन क्या कहते हैं मेटल्स है ना, तो सर वो जो हमने पहले रूल्स पढ़े थे वो तो तीन मेटल्स के अंदर चेंज हो जाते हैं.
वो थोड़े से चेंज हो
नहीं,
जाएंगे. डोंट वरी अबाउट दैट, आई विल नॉट टेक यू इनटू दैट.
ठीक है, हो गया. और सर दूसरा मुझे ये बताएं, एग्जाम में पीरियोडिक टेबल मिलेगा कि नहीं मिलेगा?
यू डोंट वरी, आपको नेसेसरी इंफॉर्मेशन मिल जाएगी जो मेमोरी से रिलेटेड. ये चीज आपको एटॉमिक वेट नहीं याद करने पड़ेंगे ऑब्वियसली. ठीक है, आई विल नॉट आस्क यू टू रिमेंबर समथिंग व्हिच इज फार्मूला आपको पता होना चाहिए, लेकिन वो इंफॉर्मेशन जो कि आप इजीली एक्सेस कर सकते हैं, आई विल नॉट टेस्ट यू ऑन दैट. क्लियर?